Hello, and in part 4 of these talks about op-amps, I want to introduce the first type of amplifier, a non-inverting amplifier, so named because it doesn't invert the incoming signal. The relevant circuit looks like this. Now, if we examine what's happening here, we can see that once again we have a potential divider attached to the output of this op-amp. And the center tap of the potential divider produces the feedback that goes back into the op-amp, but we're now back in the case where we have negative feedback. The feedback, the sample of the output voltage, is feeding back into the inverting input of the op-amp. So we can analyze this circuit. We know that the output is related to this point, the inverting input here, by the potential divider equation. And the inverting input is then the output of this op-amp, the voltage at the top of the potential divider, times, in this case, this resistor here, 1K, divided by the sum of the resistors in the potential divider, 1K plus 1K, 2K. This would just be equal to Vout over 2. We also know that our non-inverting input here is equal to our input voltage. This 1 volt signal here is just representing the input voltage. So I could write that the non-inverting input is just equal to the input voltage. And we know that the function of an op-amp is to try and put its output, a very large amount, the open loop gain, times the difference between the two inputs. If the non-inverting input is our input voltage and the inverting input is half of our output voltage, then this gives Vout equals A times Vin minus A over 2 times Vout. Bring this over here and we get Vout 1 plus A over 2 equals A times Vin. If we are assuming ideal op-amps, and therefore that the open loop gain here is effectively infinite, then A over 2 will be much, much bigger than 1. We can neglect the 1. That just gives us Vout A over 2 equals A times Vin. The A's cancel. Bring the 2 up here. Vout equals twice Vin. We have an amplifier with a gain of 2. Its output voltage is twice as big as its input voltage. We can generalize this. Supposing we have a circuit here in which the output has 2 resistors attached to it, forming the potential divider, R1 and R2. The inverting input here is then just given by the inverting input would be given by the output times R2 over R1 plus R2. That's just the potential divider formula again. Our output voltage from the op-amp, we also know, is the open loop gain of the op-amp times V plus the non-inverting input, which is just the input voltage to our amplifier, Vin, minus V minus. That's the inverting input there, which is this. So that would be minus Vout times R2 over R1 plus R2. The same algebra that we did before. That gives us Vout 1 plus A times R2 over R1 plus R2 equals A times Vin. If A, the open loop gain, is assumed to be infinite again, then this term here is much, much bigger than 1. We can neglect the 1. The 2 A's then cancel, and we're left with Vout equals Vin times R1 plus R2, keep doing that, over R2, sometimes written as Vin 1 plus R1 over R2. That's what a non-inverting amplifier does assuming that the op-amp is ideal. It's a very common and very useful circuit, and we can check that it works in the simulator again. Here is a non-inverting amplifier, and it has a gain, as you see, of 2. If I was to take this resistor up to a 3K, I would get a non-inverting amplifier with a gain of 4. And it would output 4 volts. If I took this up to 9K, I would get a gain of 10. Because 9 divided by 1 plus 1 is 10. If I wanted a gain of 2.5, then I would want the ratio of R1 to R2 to be 1.5, so that 1 plus this ratio is 2.5. I could do that by setting this resistor to a 1.5K. And then I get 2.5 times the output, and so on. This is the first of the classic amplifier configurations that we'll be looking at involving op-amps. There's quite a few more of them to come. In the next chat, we'll have a look at the second most common one, the inverting amplifier.